What up, math teacher Goat? And today's lesson in AP Precalculus is 1.10, rational functions and wholes, like you. A lot of this stuff you've seen before, but we're just talking more about the wholes today. So kind of like that movie from the aughts, the 2000 aughts, with Shia LaBeouf or whatever his face is. Make sure you click on the description, download the notes, make sure you like and subscribe, leave a comment or 2 or 15. Tell me how much you love me. And watch all of my other videos, please, I beg you. All right. Getting right into it. Find the vertical asymptotes of the following rational function. Well, what we really need to do is we need to take u and we need to factor u as much as we can. This is difference of squares. So two numbers that add up to nothing and multiply out to negative 25 are going to be x minus 5 and x plus 5. Difference of squares. Two numbers that add up to negative 8 multiply out to 15, positive 15. We'll go with x minus 5. We'll go with x minus 3. Now you look at each factor, use the zero product property, find out what your magic number is. Your 5, your negative 5, your 5, your 3. So let's label everything. 5 is up here and down here, so if there's a factor that's the same in the numerator and the denominator, that's a whole. Negative 5 is the only unique factor up here, unique magic number up here, so you're going to be a 0 because it's in the numerator. And down here in the denominator, we have a magic number of 3. That is a vertical asymptote. So the vertical asymptote is just one of them, and it's x equals 3. Now, the way we're going to start out this problem is we are going to graph f of x here and g of x here and see what the difference is between the two. Now, I'm going to use Desmos because I want to use the colors. I want to manipulate that. So I'm going to whip out Desmos, see what happens. I have a feeling I know exactly what's going to happen, but I'm not going to tell you. F of x. So f of x equals, let's do our division symbol, parentheses, x minus 3, close it, open it, x plus 5, close it, and then we have x minus 3, close it, open it, oops, open it, x minus 2. All right, standard rational, let's zoom out a little bit. Standard rational, no big deal, no big deal. G of x equals, let's put our division symbol, we've got x plus 5. I can't see what this is going to look like. X plus 5, x minus 2. What in the... What? Oh, they're the same thing. They're the same thing. Well, hold on. I did something wrong. Surely I did something wrong. They're the same thing. Oh, wait a minute. Let me zoom up a little bit. Let me get these a little bit larger. I see a factor that's the same in the numerator and the denominator. The difference between these two is this factor is now gone, but these are the same, so they would just simplify out anyway. I know what's happening. These pictures behave the same because the x minus 3 would just simplify anyway. Now, this is what happens. In this original problem, though, in f of x, I'm not allowed to plug in 3 because there's a hole there. So let's just look at the red one, see what happens when I scroll along 3. Okay, which will happen right around here somewhere. See what happens when I scroll along. Ah, you see it? Undefined. Now, will that happen with the blue guy? With Bluey here? Probably not. Oh, did I lose? There it is. Where is it? Okay. So if I go along 3 with Bluey. Nope. It was 8. It shows up just fine. So, all right. So I guess what happens is when you have a hole, you still have a domain restriction. You still can't plug in 3, but it behaves the same way as if it was simplified. So let's go back and try to explain that a little bit better than I just did. All right, so the graph of these two looked exactly the same. The only difference is you had a hole right here at the magic number 3. Okay, so when you have a hole, the graph is going to look exactly like the simplified version. Okay, that's what the graph is going to look like. You just have to have a hole at that number. So these guys behave the same. It's just with this one, there was a hole at 3. Very interesting. So let's take a look at this picture one. And we're going to look at the limit notation. Not too long ago, we looked at limit notation of vertical asymptotes. Now we're going to look at limit notation of holes. Okay, so with this guy, we have a hole at what appears to be the point 3,1. Okay, so yes, x equals 3. But if we're going to be very specific, we could say the point 3,1. As we approach 3 from the left, we approach that 1 value. And as we approach 3 from the right, we also approach that 1 value. So as x approaches 3 from the left, f of x, I guess we'll say, the f of x, as x approaches 3 from the left, the f of x is a hole. I don't know what I'm trying to say here, but that's going to be the same thing here. In this case, it's also undefined. So even though the left side and the right side limit go to the same number, the number is undefined. It doesn't exist. So maybe I should have said doesn't exist. Too late. The f of x doesn't exist. If the output values are arbitrarily close to some limit L. This is a horrible phrase, but I remember seeing a problem like this once on a practice test. If the output values are arbitrarily close to some limit L. What that is saying is as I get closer to some limit. Okay, so here is a hole, here is a hole. This is, and we'll call you L. This is me getting arbitrarily close to it. Then the hole is located at the point with coordinates CL. Okay? It is important to note that the limit from the left and right will be the same if they approach the same thing if there's a hole. So as you get arbitrarily close to a hole, you will get a hole at CL. Okay? So C would be the x value, L would be the y value. Just terrible wording that you might see on like a practice test here and there. All right, so let's see what we have here. Now we will factor this out. Okay, we will factor this out, and maybe I will try to graph this based off of the information that we have. Okay, I'm going to be cute here. Let's factor out a 10. That gives me x plus 3. Let's factor out the bottom. That gives me x minus... Nope, x plus 3, x minus 2. So what we have is we have a vertical asymptote at 2. We have a vertical asymptote at 2, like so. All right. We have a hole at negative 3. Now, I'll show you how to get to that. I'll show you how to calculate that because right now we don't have it. What else do we know? We know that if I wanted to find the y-intercept, I pretend that all the x's were 0, so that would make you 30 over negative 6. So 30 over negative 6 is negative 5, so y-intercept lives down there. I have no zeros, just holes. Okay. If I wanted to find my horizontal asymptote, I don't have one. So my end behavior is going to be 0 because the denominator is greater than the numerator. So I have a horizontal asymptote. So I do have a horizontal asymptote. It's just at 0. So I should have worded that a lot better. Okay, so what's going to happen is this is going to flatten out, okay, here and go that way, and this is going to go that way. So I'll draw this part out. But what I do also know is there's a hole at negative 3. So negative 3 what? This is going to go down here, go through there. Negative 3 what? The way you find the hole, the absolute spot of the hole, is you simplify this and then plug in 3. So you have 10 over x minus 2. Sorry, plug in negative 3. That's going to be 10 over negative 3 minus 2, which is 10 over negative 5, which is negative 2. So when I plug in negative 3, I get negative 2, which means I have a hole at negative 3, negative 2. So negative 3, negative 2, A hole is going to live right there, so you are going to look something like this. Terrible, but you get the idea. Now that I have a picture, I could do the limit notation of that hole. I could say that the limit as x approaches -3 from the left of g of x, as I go towards -3 from the left, I'm going to hit -2. Similarly, the limit as x approaches -3 from the right of g of x has me going from the right going to -3, and that's also going to hit -2. All right, all right, all right, all right, all right, all right. Numerically, now we're going to look at the same guy right here. We're going to look at the same g of x, and what we'll do is we'll use TI-84 plus this time to do the numerical part here, because I really don't want to plug that into Desmos. So let's run to our TI-84 plus and do just that. All right, here we are. Let's plug stuff in. We have in the numerator, parentheses, 10x, which is a very sweet term. It's sugar. Look it up. Whoop, I didn't mean to hit enter. See what I did? I got arrogant. Plus 30, close it, divide it, open it. And then we have x squared plus x minus 6. Now what we're doing is we really don't care about the graph. We're caring about the values that I want to plug in, the -3 point somethings and the -2 point something. So let's go to calc, let's go to value, and we'll type in. Why is my graph all the way over there? All right, we'll see what happens when I try to type it in. -3.1. Yeah, it won't let me do it because my graph for some reason wasn't centered. So why did that happen? All right, we'll go to go-to. This is a good learning experience. Zoom 6. There it is, look at that. So if you remember the picture that I drew, that's pretty dang accurate. Pretty dang accurate. It'll just have like a explosion here at -6 or -3, and that's kind of like what we're focusing on. A hole at -3, the explosion was at 2. So anyway, let's try this again. Calc value -3.1, enter, is going to give us -1.96. Should I round that? -1.961. Yeah, -1.961. Let's see what happens when I do second calc value. Let's type out -3.01. Hit enter. And that's going to get us -1.996. Let's do it again. Second calc value -3.001. Enter. And we're at -1.9996, which rounds to -2. And I basically know what's going to happen with the next one. If that's going to round to -2, then I'm pretty sure that something that's even closer to -3 is definitely going to round to -2. Hit the wrong thing because, again, I got arrogant. Calc value. All right, -3.0001. Enter, and there you have it. Okay, so this is us getting arbitrarily closer to a hole. On the other side, we're going to type out -2.9 and then -2.99, see what happens. So second calc value, -2.9, is going to give us a y value of -2.041. Then we'll do second calc value, -2.99, right? That's going to get us a y value of -2.004. Then second calc value, -2.999, enter. That basically -2.0004 rounds to -2, and I know what's going to happen when I do that last guy right there. It's going to be -2.9999, and it's going to have me round that like basically right out to -2. So what we're learning here is these values, negative 3.1, negative 3.01, okay, those are getting closer to negative 3 from the left. The negative 2.9 to negative 2.99, they're getting closer to the negative 3 from the right. And as we get closer, those numbers just flat out round to negative 2. So let's fill out that table and say what we need to say. All right, so let's fill this all in with the numbers that we came up with. When we plugged in negative 3.1, we got negative 1.961, negative 1.996, and then this basically rounded to negative 2. You basically rounded to negative 2. So we had that picture up there. Okay, so let's scroll it. As we're getting closer, okay, so we're at negative 3.1. As we're getting closer, we're basically at negative 2. Now, we'll never hit negative 2 because we're not allowed to, technically speaking, but we're getting closer. Same thing over here. This ended up being negative 2.041, then negative 2.004, and then that just rounded to negative 2, and that just rounded to negative 2, and the same exact thing happened. So that's what you're looking at numerically with situations like that as you approach a whole. You'll never approach that exact number that the whole exists at, but you're going to get awful close. So we saw something like this yesterday. All right, so let me remind you of what yesterday. In the previous video, when we had something like this, what we learned is if you have a factor in the numerator and the same exact factor in the denominator, when your multiplicity is higher in the denominator, the vertical asymptote took over. Okay, so when the multiplicity was higher in the denominator, the vertical asymptote took over. Well, I have a feeling I know what's going to happen here. So even before I read that sentence, I'm going to do some factoring with this problem and see what we end up with. We have x minus 2 squared. Two numbers that add up to 4 but multiply out to negative 12 are going to be x minus 6, x plus 6 rather, and x minus 2. Okay, so we have a magic number of 2, a magic number of negative 6, a magic number of 2. Now, in this case, we have factors in the numerator dominating the amount of factors in the denominator. What there? Well, when it comes to multiplicity, the wholes of a rational function occur at all common factors whose multiplicity in the numerator is greater than or equal to the multiplicity in the denominator. Greater than or equal to. Now, if they are equal to, we have a whole at a specific spot. So when it was x minus 3 and x minus 3, we would say there's a whole at 3, and then we're going to simplify things and find out exactly where that whole is. Now, when it dominates the numerator, when the numerator dominates, the whole exists at, in this case, 2, 0. The whole, when the numerator dominates, the whole exists on the x-axis. Okay, on the x-axis, if the numerator dominates. So, now that we know that, we can answer this question. We have a domain where you're not allowed to plug in negative 6 or 2. So let's do domain is everything up until negative 6, union from negative 6 to 2, union from 2 to infinity. The whole is going to exist at 2, 0 because the multiplicity is higher in the numerator than it is in the denominator. The zeros are going to be, well, what was this? I mean, this was a whole. This is a vertical asymptote. There are no zeros. None. No zeros. Vertical asymptote is x equals negative 6. Now we find out the horizontal asymptote by finding the leading coefficient over the leading coefficient. So we'll do x times x, which is x squared, over x squared. So leading coefficient over leading coefficient is 1 over 1, which is 1. So the horizontal asymptote is y equals 1, which means the end behavior is the limit as x approaches negative infinity, me moving to the left, of h of x is going to be at the horizontal asymptote 1. And the limit as x approaches positive infinity of h of x is going to be at the horizontal asymptote, which is also 1. That's fun. Fun stuff. Fun, fun. Fun, 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 fun. All right. All right. That's enough of that. I am approaching -3 from the left. Okay, so this is me being -3 from the left. As I approach -3 from the left, it appears that I'm going to 4.19998. So we'll estimate 4.2. And as I approach -3 from the right, I think 4.2 is a safe bet. And it's not x, it's t. As t approaches -3 from the left, the d of t approaches 4.2. And as t approaches -3 from the right, the d of t also approaches 4.2. Okay? So we have a whole mess in this problem. All right? We have a whole mess. Oh gosh, I'm punny today. -1, 2, 3, 4, 5. So this is a hole at -5, 2. We have a 0 that looks like it's only at 0. We have a vertical asymptote at what looks like x equals 2. Limits both and behaviors both go up to positive infinity. So let's see what we have to do here. Plug in 6. All right, so if I plug in 6, that is 6, right? Yeah, I guess so. If I plug in 6, it looks like 6 is going to be here. So 6 seems to also line up with 6. I don't know. My eyes are bad. You guys are good. Plug in 2. Well, what happens when we plug in 2? We get nothing, so it's undefined. Or we could say it does not exist. As I approach -5 from the left, this is me approaching -5 from the left, I'm approaching the hole, which is 2. And as I'm approaching -5 from the right, I'm also approaching 2. As I approach 2 from the left, I'm going downward, which is -infinity. And as I'm approaching 2 from the right, I'm going upward, which is positive infinity. As my x values decrease without bound, I'm going to the left. It looks like I'm going up to infinity. And similarly, as I go to the right, I'm also going up to infinity. The numbers that I'm not allowed to plug in were -5 and 2. So my domain is everything up until -5, union. And then from -5 to 2, union. And then from 2 to infinity and beyond. Toy Story. Terrible movie franchise. Terrible movie franchise. I hate it. All right. Similar problem, but just less. As x approaches 2 from the right, we are approaching a hole here. So that's going to be, I don't know, I guess we'll just estimate this. Bad job by me. We'll estimate this as 1/4. As x approaches 2 from the left, it's the same exact thing, 1/4. What happens when we plug in 2? We get nothing. It's undefined. Are all 3 values equal? No. So I guess it's safe to say that, I mean, just because the left side and the right side limit are the same doesn't mean the value itself is the same. It's not going to be defined. In fact, that's never going to be the case with a hole. That you're going to have a left-sided limit and a right-sided limit equaling the same thing, but the value itself does not exist. Very bizarre. Very bizarre indeed. Ugh. All right, let's get out the calculator. I don't want to. Do I need to? I think I need to. Well, let's see what happens. Let's see what happens. That's not factorable. There's no two numbers that add up to 90 and multiply out to 100. That's not possible. But this is difference of squares. So we have a x minus 50. We have a gross thing that I don't know what it is, but they're definitely not going to be pretty. The answers are not pretty, whatever they are. This is x minus 50, x plus 50. So what we do know just from this part, me trying to avoid running to the calculator because I really don't want to, is I have a hole at 50. I have a vertical asymptote at negative 50, and these are just ugly numbers. Zeros at ugly numbers. Zeros at ugly numbers. Okay, so a hole, which of the following, which statement is false? So a hole exists at 50, that is true, which means I don't want you. A vertical asymptote exists at x equals negative 50, that is true, I don't want you. This graph will appear linear. Let's see what happens. If I plug in 0, I get 20. If I plug in 0, I get 2. So if I plug in 0, I'll get negative 50. So you'll go away, you'll go away, you'll go away. So that'll be 100 over you'll go away, negative 2,500. So that's negative 5,000 over negative 2,500, which is positive 2. Well, how about that? So you're true, which means the lie must be the graph will appear linear. Well, the graph will not appear linear because even though these guys simplify, you simplify, and you simplify, you're still left with a quadratic over a linear, okay, which is still going to look something like this. So no, this will not appear linear, not at all. Interesting problem. It must be a homework problem or a AP classroom problem that looks like that, which is why I made it. All right, a couple more to go. Or no, these are all connected. A table on a TI-84 Plus for f of x is displayed on the right. Circle all true statements. Okay, so we have our TI. Why don't I do this? Why don't I factor u out? X minus 3, x plus 2, x minus 3, x plus 3. So I have magic numbers at 3, 3, whole, negative 2, 0, negative 3, vertical asymptote. Okay? All right. Circle all the true statements. F of 3 is undefined. That is correct because there's a hole at 3, which means it's undefined. So I need to find the exact value. We're going to use this picture for that. Ignoring the fact that that's very blurry and my eyes are bad, it looks like if these were to keep going, I have negative 0. Irregular 8.2-ish. This is, or yeah, 8.3-ish. That's 8.2-ish. That's going to be around 8.3 or 0.83-ish. 0.83-ish. Sorry that I misspoke like 50 times there. So it looks like on the left side, you'll get to 0.83. So as I go from the left, I'll get to that 0.83. So yeah, I'll agree with that. And as I move from the right, I'll get to that 0.83. So yeah, I'll agree with that. Now, here's an interesting fact. If you don't have, okay, and this is brand new, you haven't learned this. If the left-sided limit and the right-sided limit are the same, then the regular limit is the same too. If the left-sided limit and the right-sided limit are the same, then the regular limit is also the same. Very interesting. By the way, if the function has a hole, at 3, 0.83, yup. All true. All true. True. It's from a rapper in the 90s, Master P. Find the holes of the function. All right. So they want us to find the actual holes, so let's factor that out. That's going to be x minus 3, x minus 2. That's just x minus 2. All right, so I have one hole, and it lives at 2. Okay, one hole and it lives at 2. They don't want x equals 2. They want the actual hole. How do I find it out? Simplify it, and then plug in 2. So I have x minus 3, plug in the hole, which is 2 minus 3. That gives me negative 1. So after it's simplified, when I plug in 2, I get negative 1. Wait a minute. Did I make a mistake? Or is it positive 1? No, I didn't make a mistake. I did make a mistake making this problem. Silly me. There should be a hole at 2, negative 1. So I don't know what I did there. So we'll just make believe that that one is a negative 1. So there is a hole at 2, negative 1. Silly me. Silly Mr. Goat. Oh, don't let that last problem make you think otherwise. Please do like and subscribe. What you really need to do is go to my YouTube and type out AP Precalculus 1.10 and you will get my random AP Precalculus examples. Watch a bunch of them. They're good for you. They'll make you understand the content a little bit better. That's that. But yeah, we're almost done Unit 1. We have 14 lessons total. This was 10, so we're into the double dig, baby. The double dig. All right, thanks for watching. Love you both. Love you both. Love you all. Bye.